Now we're going to look at elements that can have less than an octet. So generally, carbon, nitrogen, and oxygen obey the octet rule. There are some exceptions to that, I know for sure with nitrogen. But mostly we're going to be looking at hydrogen, which we've already talked about is okay with the duet. Lithium and beryllium and boron are all okay with less than an octet. I think the trickiest of them is boron, and I'll explain why here in a second. You can also have more than an octet. We're actually not going to be drawing these, but just know that for quite a few, period 3 and lower can have more than an octet. But again, we won't draw those. Okay, so first we're going to look at, anytime we've looked at or calculated how many valence electrons we've had, they've been an even number. But you can get an odd number. So for example, here with nitrogen and oxygen, oxygen ends up having the octet. So it has 2, 4, 6, 8 electrons around oxygen, but then nitrogen only has 7, so it has an odd number. So that is a possibility. I'm probably not going to give you anything like that to draw, but that is a possibility. Okay, let me show you why boron's so tricky. So down here, boron, BF3 and BH3, boron actually has only 6 electrons around it. So normally when we would get to that point, we would think, okay, I need a double bond, but that's not the case. Boron's okay having 6. Fluorine only wants 1, hydrogen only wants 1 bond. So that's why I think those are the trickiest. So let me just draw this for you. We'll do BCl3. How about that? Okay, so boron's in the middle, chlorine's on the outside. Boron only has 3 valence. Chlorine has 7, and there's 3 of them. So we get 24 valence. Okay, so we put in our single bonds. We put in the lone pairs around the chlorines to give them an octet. So that's all 24 electrons right there. Now, normally at this point, we'd say, okay, chlorines have an octet, but boron does not. And so we would make a double bond. But that's not the case here. Okay, we're going to leave the structure alone. Boron's happy with the 6 valence electrons, and chlorine is happy with the 8. So we would just leave it alone. So that's kind of hard to do. We always want to put that double bond there. And here's some examples of having more than an octet. Again, you're not going to be required to draw those, just to show you that it is a possibility. I wanted to put it on there. So at this point, I want you to go and do problem number 3 on your worksheet. I'm not going to draw all those on this video, but I will put the answers to number 3 on Canvas. So be looking for that so you can check and make sure you drew those correctly. Okay, one last thing here. So SO2, I'm going to draw this for you because I don't like the dots there. Okay, SO2, let's draw that real quick. So S is in the middle, oxygen's on the outside. Sulfur has 6, oxygen has 6. So we get a total of 18 valence electrons. So we're going to start with our double bond. We're going to start with our single bonds and then put lone pairs around the oxygens. Okay, so there we've only used 16 electrons. So remember, if you have anything left over after you've put lone pairs around the outside atoms, anything left over goes onto the central atom. So I'm going to put those last 2 electrons right there on sulfur. Okay, so both of the oxygens have an octet, but sulfur only has 2, 4, 6. So here we need to make a double bond. So we're going to take one of the lone pairs off of oxygen and share them with sulfur, and it does not matter which oxygen you choose. So I'm going to choose this one and put the double bond there. Okay, so anytime you get a situation like this where it doesn't matter where the double bond goes, if you have several oxygens and you can use any one of them, then you know you have what's called resonance structures. So let me show you what I mean. So here, CO3 -2, carbonate ion, we have one double bond and two single bonds. Well, what we learned earlier was single bonds are longer than double bonds. But when they looked at this molecule experimentally, they found that actually all the bonds were the same length. So what happens is the double bond is not just on one oxygen, it actually gets shared between all three of the oxygens. That's why it doesn't matter which one you pick when you're drawing it, because really it's on all three of them. So if you look at this the structure at the very bottom and to the left right here, where it shows the little dots between, that is showing the double bond shared between all of the oxygens, but we don't draw it like that. We draw it like on the right side of the slide, all three structures with the double bond in each position that it can go. So going back to this one, so there were two places that we could have made the double bond. So that tells me I have two resonance structures. So anytime I draw a resonance structure, I need to put a bracket and an arrow in between the other structures. So this one I'm only going to have two. So here I want to show the double bond with this oxygen, and then I just redraw it like that. Okay, and then put the brackets. So only two places where the double bond goes, then I have two resonance structures. But back on this one, there were three places for the double bond to go, so I need three structures.